right, hello students. Looks like you guys have been working hard. Somebody shot me off a question here about number 10. So I thought, okay, maybe I'll try number 10 here. Let me read it here. It says a photon with an energy of 2.28 electron volts is barely capable of causing a photoelectric effect when it strikes the sodium plate. All right, so going back to, I guess this would be chapter 40, and we have this photoelectric effect. Remember then that as a photon comes in, it will then give its energy to this electron. And the first bit of energy we call the work function. The first bit of energy is how much energy does it take to break this electron free. Now, any energy above that then becomes kinetic energy. So using the principle of conservation of energy, we could say the energy coming in, so the energy of the photon, must equal to where it goes, which first is to break it free, and then the rest goes to give it some speed. Knowing that, then, if you ever have a photon of energy less than the work function, so some frequency, then there's not enough energy to even break it free, let alone give it some kinetic energy. And so you won't get any electrons to break free. That's why we called it a cutoff frequency in the photoelectric effect. And of course, as we were saying, that's why it made no sense to the wave model. And Einstein had to explain it with the particle model, that there would actually be a cutoff frequency, because the classical wave model says there would not be a cutoff frequency, but apparently there was by experiment. And so this is how Einstein explained it. All right, so there's the photoelectric effect, just to remind you. And so if we come back to the question, it says if a photon with energy of 2.28 electron volts is barely capable of causing a photoelectric effect in the sodium, suppose that the photon is instead absorbed into hydrogen. Now, I guess I didn't really even need to review the photoelectric effect. I thought maybe it'll come back here, but indirectly they were telling me the work function of sodium is about 2.28. Okay. But I guess they're also telling me that this photon has an energy of 2.28 electron volts. Okay? All right. So it says, suppose that this photon is instead absorbed in a hydrogen atom. Find A, the minimum N for a hydrogen atom that can be ionized by such a photon. All right, so instead of kicking the electron free from the sodium metal, we're asked to look at it kicking the electron free from a hydrogen atom. So this is worth putting down the equation for the quantization of the hydrogen atom. And as I've shown you guys in many other videos, and I'll show it to you again, this page 1221, this is what we get after a lot of work and the quantization of the hydrogen atom. And of course, then the author gives you this nice little picture here that kind of shows the energy levels. And then I kind of want to draw that here, because if I were to draw the energy levels of the hydrogen atom, and I don't know what to put down here. It's not really a two-dimensional graph. It's only energy levels. The electron gets completely free when it has zero energy. So that's taking you back to your mechanics. That's, the combination of kinetic energy and potential energy. And so something that is bound to, like a satellite, has negative potential energy and positive kinetic. And if the total of this is, less than zero, it's bound, because anything greater than zero would mean that it has enough energy to overcome the potential energy. In other words, it has enough to escape. And so the electron needs to get a lot of energy. It sounds funny. It needs a lot of energy, a total of zero, to escape. And a satellite being shot up, to escape the Earth, you have to have a lot of speed. You have to have so much speed that your total energy is zero. I always find that funny, but because this is so negative, you have to have a lot of kinetic energy to get your total to be zero and to escape. So all of our energies then are negative as long as we're bound to it. So for any value of n, you'll see you come up with a negative energy. So the lowest energy when n equals to 1 is just a negative 13.6 electron volts. And for most of the time, hydrogen likes to be in this lower energy state, this negative 13.6 electron volts. That's the lowest it can get and still obey the laws of quantum mechanics. And so that's as close as the electron can get to the proton. Otherwise, as we talked about, our quantum mechanics actually gave us a reason of why the atom is the size it is. Maybe I'll mention it again, but if you take the uncertainty in position and the uncertainty in momentum, you got to be greater than h bar over 2. And so if you try to pull the electron into the proton, which you might think because one's positive and one's negative, you make this number smaller, but as a consequence of that, that number gets bigger, and then what the electron does is gain more kinetic energy and pop out again. So the uncertainty principle gives us an explanation of why we never have the electron getting sucked in and pulled into the proton. That was one of our 5 reasons of why we need the quantum mechanics: the black body radiation, the photoelectric effect, the Compton effect, the sharp spectral lines, and the stability of the atom, the fact that it doesn't suck it in here. So that's an important piece. All right, well, moving along here, you'll see that that's pretty negative compared to this photon we're talking about. So if you were to send this photon at hydrogen that's already in its ground state, which again is where it normally wants to be, it would tumble down. But this would not be enough energy to free. You would have to give it 13.6 electron volts to completely free it. Now, if it was at n equal to 2, using this quantum here, so negative 13.6 divided by 2 squared, this is then negative 3.4 electron volts. Okay, so you still could not give it enough energy to free it when you are at n equal to 2, because you add this to this, you still don't get something above 0. So n equal to 2 is not going to cut it. But you can kind of see, and I think n equal to 3 is going to cut it. So 3 squared is 1.51 negative electron volts. All right, so if the electron is at n equal to 3, or for that matter, 4, 5, 6, 7, 8, any number above 3 or above, when you add to it a photon that's going to give it 2.28 electron volts, that's going to get greater than 0, and it's going to free it. So I guess the answer to A, let's just read A again here. It says the minimum N for the hydrogen atom that can be ionized by such a photon. So it's like n equals to 3. And so if the, again, electron is in the ground state or even the first excited state, adding this much more energy is not going to free the electron. It's not going to kick it out. It'd be similar to this photoelectric effect. It's just not enough to overcome the work function. But if the hydrogen atom has already, for whatever reason, been excited into 3 or above, you give it this much and it can now free itself. So that photon would only free electrons that are in the second or higher excited energy state. And I think that's what the author is after here. Now, in B, it says the speed of the released electron as it goes far from the nucleus. So, let me read it again. I think they are saying n equal to 3. It says the minimum A. The minimum N for a hydrogen atom that can be ionized by such a photon, and B, the speed. So I think they want to know the speed it would be released when it was in the minimum one, which is 3. Okay, now let me go to a second page and give myself a little bit of working space here. But I'm going to then say that I already have it in the minimum for whatever reason. It's in the n equal 3 state. N equal 3, I guess I should put here. That was a terrible way of writing it. So at n equal 3, this is the current energy. So the total energy, okay, would then be the amount of energy it currently has plus the 2.28 electron volts that it is now going to absorb. And you can see that that number is, of course, greater than 0. So 2.28 and then add a negative 1.51, and there's going to be an extra 77 or 0.77 electron volts, and that extra stuff would be showing up as kinetic energy. So in other words, it needed enough energy to break free. That gives us to the 0, and then this is the extra. So I could say then that the kinetic energy, which is 1/2 mv squared, is equal to 0.77 electron volts. And so again, we're looking for this speed. Let me then change it into joules by reminding myself here how much is a electron volt worth. So times 1.602 times 10 to the negative 19 gives me this many joules of energy, which is joules is good because that would be units of kilogram in meters per second squared. So let me move the 2 over, so times 2. Let me move the mass over, so divide by the mass, 9.11 times 10 to the negative 31. So that would be velocity squared. Let me then take the square root of this. And so we're looking at a velocity of 5.20 times 10 to the 1, 2, 3, 4, 5 meters per second. So it would, like I said, it would have enough energy to eject it and a little more. And that little more is going to show up as kinetic energy, and it's pretty high speed. It really doesn't take much energy to make these electrons go at a high speed because they are really tiny and very, very small mass. And so just a little bit of energy and they go really, really fast. In fact, we got away with just using the kinetic energy in classical physics because it wouldn't take much for this to be equaling 10% the speed of light. We're still 100 times smaller than the 10% the speed of light, right? The speed of light is 3 times 10 to the 8th, so 10% would be 3 times 10 to the 7th. We're roughly 100 times, maybe more like 60 times smaller than that. But that's okay then. We can use 1/2 mv squared. But a lot of times for electrons, you do have to go gamma minus 1 mc squared because, look, it doesn't take much energy for these things to get really, really fast. All right, hope that helped. There's part C? No, that's it. All right, enjoy.